are welcome to use the exact same simplification to make your algebra easier, which is that I will choose my coordinate system to be centered at the initial time. This allows me to write right away y naught is equal to x naught is equal to 0, which means that I don't have to carry x naught and y naught through my equations. So it simplifies the algebra. If you don't want to do this, that's perfectly fine. But in order to simplify the equation, I would suggest use that convention. So as you derive it, just show me a little diagram, tell me where you put your coordinate system, then you can assume the particular initial value of your position, and then as you derive the equation, the whole thing is much simpler. Okay? So I will always, since I'm picking this coordinate system, then I will assume that A is equal to minus G in the J direction. And that's the important part for projectile. We're still assuming that we're dealing with a free fall type of situation, which means that we neglect air friction and the acceleration is pointing down. Due to the choice of my coordinate system, I can express my acceleration in the J component. So it's very clear that there is no acceleration in the X component or in the I component, which means that all the vectors along this trajectory will only be affected in magnitude in the Y direction, but never in the X. Okay, remember that by definition, A is equal to dv dt. So if A is in the Y direction, the change of magnitude of the velocity will be changed only in the same direction as the acceleration, and therefore only in the Y direction. And we've seen that in 3D. As you go up, the velocity decreases because acceleration is against it. As it comes back down, the magnitude of the velocity increases because the direction of the acceleration is in the same direction as the velocity. But in the X direction, even though our object is moving towards the right, therefore in the X direction, since there is no acceleration in the X direction whatsoever, whatever initial velocity we have at t is equal to 0 better be the same at all time. Therefore, v0x must be the same as v1x, which must be the same as v2x, and v3x, and v4x, because again, the acceleration is only in the y direction. So this tells us that the equation of motion that we will derive will be different whether we deriving the one in the x or the y direction. So we'd like to go through both of them. Okay, so first let's start with the simplest case, which is the x direction. Oops, one more board. Again, we'll use the exact same starting point. A is equal to dv dt. So again, as always, if there is any step that you're not sure or you would like me to repeat, please stop me. Use whatever, this symbol or this symbol, whatever, or raise your hand, whatever it takes. Okay? Okay, so in the x direction, since A is perpendicular to the y direction, if we look at the x component of the acceleration with respect to the x component of the velocity, we have ax is equal to dv dt. And this v must be the x component of the velocity. I'm going to do the same technique as before. I'm going to multiply everything by dt, and I have ax dt is equal to dvx. Then I'm going to integrate both sides. Then I'm going to put my initial and final condition, or born of integration. Since my dummy variable on the right hand side is vx, my initial value will be v naught x, and my final value will be vx. But again, if my final value is vx, I need to change my dummy variable to say vx prime. Similarly, on the right hand side, my dummy variable is t. I'm going to start t is equal to 0, which is 0 by convention, and my final value of t, which is t. Therefore, I need to change my dummy variable name t prime. Okay, and at this step, same as before, we need to ask ourselves, right hand side, no problem, but left hand side, we need to know something about ax. If ax is 0, no problem. If ax is a constant, we can take it out. If ax is a function of time, then we can integrate it. If ax is a function of position or velocity, we're toast. we have to go back and use a particular trick, which we'll see in the next chapter, and the trick that you will relearn in 271. So in your case, since A is along J coming down, the AX component of A is 0. Therefore, AX is 0. Bang! Which means that the left hand side is 0. Bang! Right hand side is trivial, Vx minus V naught x, and therefore Vx is equal to V naught x. Now at this point, we know what V naught x is. V naught x, by applying the technique from chapter 3, if we know V naught and we know theta, then we can decompose our vector V naught as V naught x and V naught y. So right from the beginning, we can express the functional form of V naught as V naught x I plus V naught y j. The V naught x in magnitude will be V naught cosine theta, and the magnitude of V naught y will be V naught sine theta. Since V naught and theta are given to us initially, they're both constant. Those two vectors component are also constant. So you have the choice here. Either you put your V naught x directly in your integration, or you leave it as V naught x and you plug it at the end. But you definitely do not want to leave V naught x undefined. So at some point, you want to replace it by its value, which is expressed in something that's given to us. In this case, V naught or theta. So what does that tell us? It tells us that at any time, remember, we're shooting for velocity of x as a function of time. Same as before. That's when we start with a is equal to dv dt. This is telling us that at any time, the velocity in the x direction is entirely independent of time and is always going to be equal to v naught cosine theta. So if we want to plot vx versus time, then whatever v naught cosine theta value is, something positive, it will always stay the same. Which makes sense. If v naught stays the same, then a must be 0, because a is, when a is non-zero, v changes as a function of time. So it's all consistent. So far so good. Pretty useless, but at least it's consistent. Okay? So now the next part of the game is to develop and derive the position as a function of time in the x direction. We're going to use the same technique as before. We're going to start from the definition. Vx is equal to dx dt. We're going to multiply both sides by dt. Vx dt is equal to dx. Integrate both sides. Now, if you have chosen to set up your coordinate system in the same way as I did, then right away, you know that x naught and y naught is equal to 0. You can use this in your derivation if you want to. You can use it at the step where you're at, x naught, right here, or you can put it at the end. You decide. So I'm going to leave it as x naught for now, and then I will replace it by 0 when I'm finished. Again, you can decide whether you put 0 here directly, or if you evaluate x naught at the end of the equation. Up to you. So here my dummy variable is t, 0, t, therefore t prime. Right hand side is trivial, x minus x naught, but the left hand side, same problem as before, we need to know some information about vx. But we know vx, we just derived it, so we can plug it in there. We know that this is a constant, therefore we not only can replace vx by v naught cosine theta, but we can also take care of the integral. So this becomes v naught cosine theta integration between 0 t dt prime is equal to x minus x naught. And as we integrate this trivial integration, we end up with x minus x naught is equal to v naught cosine theta times t. And if we solve for t as a function of time will be x naught plus v naught cosine theta times t. This is very similar to what we've done in one dimension. The only difference was that we didn't have the cosine theta. Since due to my chosen coordinate system, my x naught is 0, then I can get rid of x naught, and therefore in this particular case, due to the choice of my coordinate system, the functional form of the position as a function of time is nothing else but v naught cosine theta t. So at t is equal to 0, obviously this equation is verified. 0 times v naught cosine theta is 0, therefore the initial position is 0. And then as t increases, x is going to increase linearly, because this looks like a line equation, right? If you plot x versus t, this is the same as having y as a function of x. V naught cosine theta is nothing else but the slope. If your x naught is not 0, you will start somewhere in the x-axis. In my case, x naught is 0, so I'm going to start at the origin of my coordinate system. My slope is obviously positive if my theta is between 0 and 90, and therefore I would expect a straight line, because again, this looks like a straight line, mathematically. So I expect something like this. Okay? Questions so far? Okay, so let's give them some numbers, so in case we need them, we can always go back to them. Whoops, that's maybe 2. Ah, questions from Jishurum. In the x direction, nothing. It's the absence of the acceleration. So, it's actually a great question. If you have, we will see in further chapter something that will make more sense because it will relate with something we're all used to, which is concept of force, or as John suggests, concept of momentum. For when we only do strictly kinematic, all we have is the definition. So if we look at the case of a big interval, whenever there is an acceleration, there is a change of velocity. Okay, remember that we are only dealing with cases where we go forward in time, so delta t is never 0. A delta t is equal to dv, and this one is never 0. So if a is non-zero, then obviously delta v is not going to be equal to 0, which means that the velocity is going to change. If a is equal to 0, then from this equation we are forced to accept the fact that dv is equal to 0. Now delta v by definition is always the final minus the initial. V final minus V initial. If we use the exact same notation as the one we've been using, it means that V minus V naught is equal to 0, which means that V is equal to V naught. If this is true, since x is equal to delta V delta t, we can use again the exact same reasoning. If V is a constant, by definition of the relationship between V and x must be increasing at a constant rate. But if E is not a constant, then x will be changing with a behavior such as x to the 2. So when you have an acceleration present, such as free fall, and you go against the acceleration, your change of position is never going to be linear. Your change of velocity will be, but not position. As you do projectile and you're looking at the x direction, since the x direction has 0 acceleration, the velocity is constant, and therefore the position has to increase at a constant rate. Does that make sense? Ah, good question from John. If x is equal to dv dt and dv is 0, wouldn't x never change? Good point, good point, good point. Let me think about that one. Yep, that's a math question. That's a math question. Let me think about this. Let me think about this. I'll take a brain check and I will think about it tonight and I will get back to you via email. Because I have a little brain fart just now on that math aspect. So I'll look into it, I'll think about it, and I'll get back to you. Jishurum, is that explanation satisfying or would you like to investigate it some more? Okay. Jeremy might have an explanation. Go for it. Okay. Yeah, it seems to be a math issue. Uh, Let me think about it and I'll get back to you after class. Okay, so what did we do so far? We've obtained the velocity in the x direction as a function of time, and we've deduced the position as a function of time. Velocity is a constant in the x direction, which tells us that graphically v naught x in length is the same as v1x is the same as v2, since v2 is entirely in the x direction at the highest point, which is also equal to v3x, which is also equal to v4x. So the nice thing about this direction is this is, remember, the equation out of the four, this one, that we could only use if a was equal to 0. Remember in 1D we had x is equal to vt, or x is equal to x naught plus vt. And I was stressing out the fact that this is the only equation out of the four that we can use if and only if the acceleration is 0. That's the one that we see again. So in free fall 1D, there was no possible case as you go in the free fall situation that we could use that equation. In the projectile motion case, we are not able to use that equation if we investigate and analyze the motion in the x direction. So let's do the same thing in the y direction. Let's start with the same starting point. A is equal to dv dt, but this time we're concerned about the y direction, so ay dvy. Multiply everything by dt, ay dt is equal to dvy. I'm going to integrate both sides. This is v naught y, which is also v naught sine theta. The top is v naught vy, therefore I'm going to put a prime, t prime, 0, t. And now the next question is, what is ay? Oh, ay, 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 ay. Thank you, thank you, thank you. So that solves every problem. If v is equal to v naught, this is a constant, therefore delta x is equal to a constant times delta t, which is the same as y is equal to mx. Thank you, sir. Thank you. Thank you for catching my goof. All right, problem solved. Okay, so at this point, here again you have the choice, same as 1D. Either you keep a y until the end and then you replace a y by either g or minus g depending on your choice of your coordinate system. Since I have already defined my coordinate system, I'm going to replace ay by minus g automatically. So I'm going to have minus g, which I can also take out of my integral because it's a constant, 9.8. And keep in mind that if I put my negative sign due to the choice of my coordinate system, if I ever need to substitute g with this value, I need to substitute g as positive 9.8. Okay, remember the acceleration due to gravity g is always positive 9.8. Negative sign comes from the choice of your coordinate system. And then we can integrate the rest easily, which is trivial. We've done that hundreds of times already. The left hand side will give me t minus gt, and the right hand side will give me v naught vy minus v naught sine theta. So as I'm solving for vy as a function of time is going to give me my initial value of the y component of the velocity, v naught sine theta, minus gt. Again, very similar functional form as before. The only difference is we didn't have the sign in 1D, which makes sense as we give an initial velocity in y direction. This is the highest term. At t is equal to 0, we don't have the second term. As t increases, the second term will become bigger. Since it's multiplied by a negative sign, it will minimize the value of the initial component of y, and therefore the overall will decrease. As t becomes even bigger, there is a point where gt will be exactly the same as v naught sine theta, which means that the vy will be 0, and we know we're reaching the highest point. And as t increases again, the second term will become bigger, therefore the overall will become negative. That's when we're going down into the process. So as we plot this, we recognize that this is the same as y is equal to mx plus b. M is minus g, x is t, and plus b is the y-intercept v naught sine theta. So if we plot vy as a function of time, we need to start with a positive value v naught sine theta. The slope is negative, negative g, and this little point will refer to the point of the highest position in that particular trajectory. Okay? Now, let's keep going and let's obtain the functional form of the position as a function of time. Same as before, we're going to start with vy is equal to dy dt. Okay, I was just a little bit worried that I did the opposite again. Yeah, that's correct. Okay, so let's multiply everything by dt. Vy dt is equal to dy. Integrate both sides. Start at 0, t, t prime, y, y naught. But due to the chosen coordinate system, I can put a 0 here, bang, and y. And now the next question is, what the heck is vy? But we just derived vy on the previous question. Vy this time is a function of time, so I need to keep it into the integral. I cannot take it out. So this will become 0t v naught sine theta minus gt, but my dummy variable is t prime, so t prime dt prime is equal to the right hand side. We can integrate it right away, y minus y naught, and again let's get rid of the y naught once and for good, once and for all. Now right hand side, this looks a little bit messy at first, but when you think about it, it's actually not too bad. Let's rewrite it here. We have to integrate v naught sine theta minus gt prime dt prime. Remember, t prime is your dummy variable. That's the only thing you care. So as you look at the functional form of what you need to integrate, that's your variable. The rest, as far as this variable is concerned, are just constants. And sure enough, from a physics point of view, we know that those two guys are constant. V naught is constant, sine theta is constant, and g is constant. So technically, this is the same as having, say, 3 times sine of pi over 3 minus 5x dx. Exactly the same as what we learned how to do in Calculus 1. This is a polynomial integration that's trivial. All we have to do is take the first term, multiply it by x, second term, x2 divided by 2, 5. So same thing here. The only thing we have to do now is train our brain and our mind to recognize that we're not dealing with x and y anymore. We're dealing with a new variable t prime, which means that every other variables, as long as we're sure that they're constant, we just treat them as constant. Okay? So, in the previous screen, oops, what is my previous screen? Then v naught sine theta is just a constant. Therefore, as we integrate it, we just multiply this term by t prime. gt prime, as we integrate it, become minus gt t prime divided by 2. Whoops. T prime squared divided by 2. And we're going to evaluate this between 0 and t. I'm not skipping that step because I'm dealing with a polynomial. I mean, a more complicated function as just a constant. I want to keep that step because in general, you have to be careful. If you're dealing with polynomial, usually if you have a constant term, you can only worry about the top one. If the bottom one is 0, then it's trivial. But if you had a constant term, you would have to be careful because the constant term will survive as you evaluate with both values. And this becomes even more important as you're dealing with exponential function. Between 0 and any value, the 0 will not give you a 0 value. Most likely it will give you a 1 value because e to the x, as you evaluate as x equal to 0, will give you 1. So that's why I'm being a little bit careful here. So, but in this case it doesn't matter since every term as the variable, as I evaluate with 0, they will all go away. So the only one that will survive are v naught sine theta t minus 1 half gt squared. And this is equal to y. This is my, and then if we rewrite it in order, quote unquote, lowest term first, and then the highest, we end up with this, which again is exactly the same as in one dimension, but the only difference is our sine theta. Now let's look at this. This is telling us that now that we have an acceleration in this direction, the velocity increases at a constant rate, but the position would increase as a function of degree 2, same as one dimension. So if you were going to plot y versus t, then you would have either a parabola that looks like a U or an inverted U. And again, in order for us to differentiate if it's a upside U or a downside U, I guess, is by looking at the sign of the term that multiplies the highest term. In this case, the term that multiplies the highest t is negative. Due to this property, we know that we're dealing with an inverted U. Same as before. Everything that we derive in the y direction should be exactly the same as the one-dimensional case, with the only difference of the component of the initial velocity. The rest should be the same. And again, this point, the highest point, refers to the point of the crossing intersection between Vy and t in the other description of the motion. Okay? So, we've just derived same equations in 1D, Vx as a function of time, x as a function of time, Vy as a function of time, and y as a function of time. So all our equation, let's give them some numbers. Let's call it, let's call this 3, and let's call this 4. We know that all those equations are a function of time. So time acts as the parameter. But it's kind of boring because sometimes, or pain in the butt, because sometimes some of the problem will not give you anything about time, which means that we're going to have to use two equations to get to the answer that we want. Which means that, in other words, we will not be able to find a single equation that will satisfy what we have and what we're looking for. There will always be a stupid time in a way that we don't know, which means that we are going to be forced to use two equations to get what we want. Solve for t in one of the equation, substitute it in the other, and get what we need. So, let's do it ourselves and see what happens. In other words, let's obtain the functional form of the position as a function of x. That is, we want to get rid of all possible time whatsoever. How are we going to do this? Well, let's go back to our equation. We know we want to start with equation 4, because equation 4 has the y. And we know we want to express y as a function of x, so let's look for another equation that has x. Obviously, not equation 3. Let's look for another one. Not equation 1, equation 2. So if we combine equation 2 and equation 4, equation 2 has x, equation 4 has y, all we have to do is get rid of time. So possibility is solve for t from this equation and substitute it into this equation. T here, t here. Then x will show up here, x will show up here, and we will have y as a function of x. Or we solve for t in this equation, and then we substitute it into equation number 2. But this is a quadratic, so that will take much longer. Let's use the lazy way, and let's start from equation number 2. Let's solve for t, and then let's replace t by the new value as a function of x in the equation 4. So let's memorize that equation. X equal to v naught cosine theta t, because I'm gonna have to switch board. Oops. So since x was equal to v naught cosine theta t, as we solve for t, t is equal to x divided by v naught cosine theta. And I remember that our functional form from y was y is equal to y naught, but y naught was 0, plus v naught sine theta t minus 1 half gt squared. So all we are going to do is, whenever we see a t, oops, I forgot a t, t here, we're just going to replace all the t's by this new functional form of time. So my equation 4 will become v naught sine theta times x divided by v naught cosine theta minus, whoa, so I guess g, I have a 2 here, and then t is being squared, so I need to square everything. X squared v naught cosine theta. Looks a little bit messy, so let's try to clean it up. We realize that we can simplify v naught, and for good luck, we could replace sine over cosine by tangent. So y would be equal to x tangent theta minus g over 2 x squared. Oops, bang, and I forgot, thank you. I forgot my squared. Oh, I shouldn't put my 2 here, let's put it here. Otherwise it might be misleading, as the 2 might be attached to the theta. 2 v naught squared cosine squared theta. Okay, so far so good. So this is the equation of y as a function of x, which is nice because then we don't need t. So if we're dealing with the problem where no t is given, but x, and we're being asked for y position, easy. And again, as you plot this, same as y versus time, this again is a parabola. The term that multiplies the highest term, x squared, is negative, minus g, over 2 v naught squared cosine squared. Therefore we know, same, it's a parabola with inverted u. Now, the next step is ask ourselves an important question when we actually apply this to, I don't know, bowing, like when you play with a bow and an arrow, or rifle, or any time you try to shoot at something, like wild pig or whatever. You might want to ask yourself, let's say I'm dealing with a rifle that has a particular capacity, so technically has a particular power, my V naught is pretty much fixed, depending on the or whatever gun that you have. But you want to shoot that bullet on that target the further away possible. Therefore, you want to have the largest X value as possible, this one. But you stuck with V naught because it's embedded to the type of gun that you're using. What would be the most efficient angle that you should use? Good question, good question. Yeah, excellent. So our intuition would be 45, either from practice or we've heard it before. What is powerful about kinematics is we're going to be able to derive this particular value only through mathematics and without having to do with experiments. Let's do this. So, but for us to be able to know how we're going to do this, let's go back to our, oops, if I shoot 45 degree, then the target wouldn't even get damaged. Ooh. Ah, yes, 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 you're right. We are, yes, yes, yes. We are not involving newtons yet. So from a strictly kinematic point of view, you totally agree. If you shoot a little bullet of 3 gram, it ain't gonna hurt the target that much, because we haven't considered the mass or the aspect of Newton in there. Is that what you meant? Okay, okay. We'll get there next chapter. For now, we only concerned about being able to reach the particular target and decide and derive mathematically using the power of this particular model and theory how we can obtain the optimum angle. Before we get to this problem, let's go back and review calculus. If you have a function f as say, a function of x, this is your y, and you're wondering what is the value of x such that y is max. This is a perfectly valid question that most likely you've done in Calculus 1, towards the end of Calculus 1 or at the beginning of Calculus 2. This is a strictly mathematical problem. You have a function y defined in terms of a variable x, and you're wondering what would be the value of x such that your y is maximum. Well, the recipe in calculus is to take the derivative of y as a function of that particular variable, dx. That's the first thing that we do in calculus 1, step 1. And step 2 is to set this equal to 0. Step 3 is to actually solve for x once you've done that. And then step 4 is to take that x that you just obtained, put it back in your original functional form of y, and this will give you y max. Okay? That's the recipe in calculus. And that's exactly what we want in physics. We have an angle. Whoops. Oh, I just lost my pen. Ay, ay, ay. Okay. Okay. I'm back with my pen. So let's take a break from the lemmings. I thought it was some kind of beast from Harry Potter or something. Okay. So in our case, we want to relate this to something like we would like to figure out the optimum angle such that x is max, which is very similar to what we've done. What is x such that y is max? Excuse me. Meaning, we need to find a way to express x in terms of theta. But we're almost there. If we look at the previous, whoops, where was I? Here. Functional form of y as a function of x, there is a theta in there. And this is where we're going to make another approximation based on the situation that we're dealing with. And you're welcome to use the exact same situation if you're being asked to derive such a functional form in the test. Remember that in my original graph, I landed here in the exact same level as I started. Okay? So this particular point B happens to follow this path and be on this path the same way as this point B is on this path. Correct? So in this particular case, where I simplify my problem versus the beer pong problem that John was mentioning where the incline is like this, then point B would be down there. The y position of B is exactly the same as the y position of my initial point, which means 0. So if I'm looking for the maximum range, I know that the point or the maximum x value of this point is a point whose y value is also 0. Now, this is to simplify our calculation and to obtain the 45-degree angle. If you have an inclined plane, the method is going to be exactly the same, but we won't be able to make it as simple as what's going to happen. So, mathematically, let's make another parenthesis. If you have a function, f1, and you have another function, f2, and you're looking for the point where they intersect, point A. Then from, I guess, math 140, 135, so algebra and function, what you do is you know that A of coordinate xa and ya is on the function f1. Therefore, if f1x is defined as such, you know that if you replace the xa for your x and your ya on your y, it will satisfy this equation because a is on the function f1. Similarly, is a if a is on the function f2, as you substitute the coordinate of a, oops, 2, in this new function, it will also satisfy this equation. So since you're multiplying, you substitute ya in y1 and y2, then it's the same as doing, I can just equate f1 with f2, and this will give me the position of a. And then you can replace a in either f2, I mean x in either f2 or f1, and you'll get the y of a. Correct? So this is from basic function analysis. For our case of a projectile motion, we have two functions. One like this, which is y over x, which was original v naught sine theta minus g over 2 blah 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 squared cosine squared theta x squared, and I forgot an x. This is this function, and our point, which refers to our maximum range, also lie on this function. And the functional from this function is nothing else but y is equal to 0. So if you're looking for the maximum range or the x position of b, all we have to do is equate this function with this function, and then we can solve for x. Okay? And since when we do this, we're only going to be left with theta, theta, and x, this will give us the functional form of x as a function of theta. That's what we're going to follow. To make another parenthesis and echo the beer pong problem where the table is inclined, if you're looking for where the beer pong is going to land on the table, which is this point B, then you're going to use the exact same technique. You know the functional form of your projectile motion, the same as this, and all you have to do is figure out the equation of this line, which in this case might be something like minus, I don't know, 3x or something. And then you're going to equate this with this and figure out the position at which the pong lands. Same technique. The only difference between this case is now you have minus 3x, to which you'll have to combine with the first term. While in our case, since we're going to be landing in the same position as the one we're starting with, we get y with 0, and our equation is much simpler. Okay? But the technique will be the same for the beer pong problem. So, let's do it. We were here, and we would like to equate this with this equation, y is equal to 0. Because again, this refers to the point at the intersection of two functions. As we equate the y value, we can solve for the x, which will give us x, or the position of this particular point. So as we do this, we have 0 is equal to x tangent theta minus gx2 divided by 2v naught cosine squared theta. Mathematically, we have two solutions. We can factorize x out, and we have x times tangent theta minus gx divided by 2v naught squared cosine squared theta. And mathematically, this says that either x is equal to 0 or tangent theta minus gx blah 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 is equal to 0. Both solutions are correct mathematically. Physically, they're also both correct, because remember, those two functions intersect at 2 points, the one that we're interested, but also the initial point. And this is this solution, x is equal to 0, gives us the initial point, which in our case, we don't really care. We're more interested in the other one, and therefore the other solution, so we're going to set this equal to 0 to investigate the other solution that is more interesting. So in this case, we can solve for x, and we have x is equal to tangent theta. Oh, it's going to be messy. Let me rewrite this on a new page. we have tangent theta minus gx 2 v naught squared cosine squared theta, and this is set to 0. So as we solve for x, we end up with, I'm going to replace and rewrite tangent as sine over cosine. And you might wonder, now why do I put it back as sine over cosine? Well, I converted it earlier as tangent. It's because I know what's coming ahead, and I know there will be a nice simplification. So we have sine theta divided by cosine theta, that's my tangent, which I moved from here to here, or I move this guy here and I replace my tangent by sine over cosine, and now I need to multiply my sine over cosine by this term and divide it by this term. So 2 v naught squared cosine squared theta divided by g, and that's my x. And on the reason why I replace and retransform my tangent as sine over cosine is that I can nuke one of the cosines, bing, and I can recall what I've learned from Math 140 by recognizing these burgers. And remember that 2 times sine times cosine is, oh, bugger, sorry, bugger. Don't make me hungry now. I haven't eaten it yet. So this is equal to x, almost. Yeah, sine 2 theta. And the reason for this is because if I leave x in function of theta and there is several thetas, as I'm going to take the derivative of x with respect to theta, it's going to get messy. And remember, that's where we're going towards to. So if I can combine all my terms that involves theta into one, then as I take the first derivative of x with respect to theta, it will be much simpler. That's the reason for this trick. Okay? So again, you don't have to use that trick, but you will see that if you don't, the algebra will be a bit more complicated because you're gonna have to use the chain rule and blah 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 blah. So here we end up with v naught squared sine 2 theta divided by g, which is nice and pretty. And that's my x as a function of theta. Okay, now let's recall what we had investigated earlier, if I can find it. There. Now we have x as a function of theta, which is the same as before, y is a function of x. We want to figure out theta so that x is max. Therefore, if we follow the same recipe, since we have x as a function of theta, and we're looking for theta such that x is max. Oh, question for head. Equation 1 was Vx is equal to V naught cosine theta. And equation 4, if I recall, was y is equal to V naught sine theta minus g over 2 t squared. And I forgot a t. This was equation 1, and this was equation 4. If you're referring to the equation of motion, right? Equation 4 and equation 1. Oh, equation 2, I'm sorry. This is the equation 2. Yes, we use equation 2 and equation 4, Roger, yeah, exactly, in order to express the functional form of y as a function of x, which was this one. So this equation was obtained by combining 2 and 4. And then we calculate the intersection of this equation that we obtained from equation 2 and 4 and the equation along the x-axis in our particular case, because we are landing at the same height as where we started. That's how we got this. And then we solve for it and we got the functional form of x as a function of theta. And now we can use what we've learned before with calculus. We're in the same situation as before. So all we have to do if we follow the same recipe as calculus is to take the first derivative of x with respect to theta. That's step 1. Then equate this equal to 0, that's step 2. Then obtain the x, that's step 3. And then let's put back x into the original equation, and we get the theta for x max. Nope. Yes. I'm sorry. Yes. Remember, you given all the equation from chapter 2 and chapter 4. They're already on the website. If you go to Kinematic 1D, the last link is always formula. If you scroll all the way to the bottom, you have the PDF version. But in addition to being able to use the equation given to you on the formula sheet, which will be at the end of your test, there will be one question on the test that will ask you to derive those equations of motion, as John pointed out. Okay, but as you apply those equations to solve problems, please don't rederive them. Otherwise, it will take you forever. But the reason why, again, I like you to go through that process is because in a year from now, in 271, most likely in 80% of the problem, you will have to rederive all the equation of motion this way. Except it's going to be a little bit more complicated because time is not going to be the only parameter. Okay? Okay, so let's do this step. I was here. Yeah. So let's take the derivative of x as a function of theta. I can safely take the full derivative. I don't have to take the partial derivative because all the other variables that shows up in the functional form of my x equation are all constant. If you notice a constant, g is a constant. So I don't have to take the partial derivative of x with the partial derivative of y of theta. Straight derivative is perfectly fine. So v naught squared and g are just two stupid constants, so we can just have them tag along. And really, we're interested in the sign of a derivative of sine 2 theta. Here, obviously, we have to use the chain rule. Chain rule. This is going to be your bread and butter. So make sure that if you didn't like it in Calculus 1 or were a bit fuzzy, go back to it. Science is using the chain rule over and over and over and over. Okay, so in this case, we're facing such a situation. We need to take derivative of the envelope function, sine. Derivative of sine is cosine. Cosine 2 theta. And then we need to take the derivative of the inside function, which is 2 theta, and the derivative of 2 theta is 2. So we have another extra 2. Okay? Is everybody okay with that step? The chain rule step. Right on. So did I, how come divided by 2? Jeremy suggests divided by 2. Um, uh, let's, oh, okay. You mean times 2. Okay. Yes. That's for integration. Okay. So we're on the same track. Okay, good. So now remember when to set this equal to 0. That's easy. Remember our variable is theta, so we can nuke divided by 2, multiplied by g, divided by v naught squared, bang, and we end up with cosine 2 theta is equal to 0. When is this going to be true? For which value of 2 theta is a cosine equal to 0? You skipping a step. This is our variable, 2 theta. Yes, when whatever is applied by the transformation of cosine is equal to 0, it means that our 2 theta, or whatever big X, is pi over 2. Because we know that cosine of pi over 2 is 0. Yeah, sorry. I'm still on the 2 theta step. Okay, I want to make sure that everybody understands that really little tricky step. Now, technically and mathematically, we have all possibilities. Right? Pi over 2, 3 pi over 2, 5 pi over 2, they all will give us 0. They will all satisfy that equation. In our case, since we have defined a coordinate system going like this, then our angle theta is between 0 and 90. We cannot go 3 pi over 2, otherwise we're shooting into the ground and then we have nothing. So 3 pi over 2 is out. But we could have 5 pi over 2. 1, 3, yep, 5 pi over 2 would be the same. Okay, so since our theta can be always reduced to an angle between 0 and 90, from a physics point of view and due to the choice of a coordinate system, we can only keep the n is equal to 1 case. So it's really pi over 2. And then you solve for theta, pi over 4. And bang, that's our 45-degree angle. That's nice. It's very, very nice. Okay? So that's the straightforward method following the tools that we learn in calculus and being able to enjoy how we can use them to solve a physical problem. Now, you could have gone a little bit faster than this. If you look at this functional form of x as a function of theta, you're looking for x max, right? Now you know that v naught is a constant, so v naught squared is never going to change. Same for g. So really, when x is max, it only depends on this factor, sine 2 theta. And you know by definition of sine, and the property of a sine or cosine function, that it takes either its maximum value as 1 or its minimum value as minus 1. So you can go from minus 1, 0 to 1. Since you're looking for x max will be, x will be maximum when sine will be maximum. And we know that the maximum value of sine is 1. Therefore, when sine is 1, sine of 2 theta is 1, is exactly the same as theta is equal to pi over 4. Okay, because as you solve for this means that 2 theta must be equal to pi over 2. And therefore, theta is pi over 4. And you can bypass that whole technique, which is the most general technique, but in this case, it's a little bit overkill. Okay, so you can shortcut your derivation that way if you want to. Okay, so you have the two options. And again, we have, and then let's finish it up. Since theta is equal to pi over 4, then we can plug in it back into our x functional form, and we will obtain the maximum value of x, which in this case is obviously v squared over g. That's our maximum range, which is for sine 2 theta being 1 or theta being 45. Okay? But remember, the very important aspect of this is where we've made the assumption and which one. Remember that we made a major assumption earlier right here. When we made that step, we set our equation as y as a function of x equal to 0. And we did this because we're landing at a point whose y-coordinate is the same as the initial point. If you were dealing with a case where the inclined plane was going down or going up, then you will need to figure out the functional form of this line and then replace it by y is equal to 0. So your x term will be a little bit more complicated, but not much more. Okay? It would be a pain in the butt if you had something like this, because then you have a y-intercept as well. Then you have to use a quadratic equation to get x. But mathematically, the steps mathematically are always the same. The algebra would be a bit more involving depending on which surface you're dealing with. Okay? Let's say you have a table like this, and you want to shoot on a table. Questions on this?